let's start with today's class. Okay, so the previous classes what we studied. So in the previous classes we studied about the we started with the dynamic power dissipation, and we started with the switching power dissipation. As you know that what is the switching power dissipation? The switching power dissipation is a power required to charge and discharge the output capacitance of the gate. Then we studied in that we concluded with what will be the internal load power. So we calculated the energy, the transition for the internal load is nothing but CI into VI into VDD. But if I go for a complete switching, so what I will do later, I will tell about that what will be the complete switching. Before entering into that, we need to study about the switching activity of static gates. The switching activity of static gates, in the sense it is like the, I can say what is the meaning of that. So that will be mentioned like the output of static CMOS or output static CMOS gate depends on the function equivalence. Okay, so example like I can say, I'm going to say output of y is equal to a b function. Like using these two inputs a and b, I can realize any basic gates. That is the meaning of that. Right? So it is assumed that the independent of each. So it's like assume that the inputs are independent to each other. The probability of occurrence so what will be the output I'll get? The logic gates at it can be either 0 or I'll get the output is 1 only. Is same. So now we can see, now we have to assume that the inputs are independent of each other and the probability of occurrence of 0 and 1 is same for the various inputs. So now what we will do? Let consider or let us take that also I have to teach you. You come to campus, I will teach you. Let what is the peanut? You take the peanut. The peanut is here. Sorry, will not solve anything. I'll take a screenshot and I'll send to your parents also. Probability that. And I will forward it to Dean also. So don't try these things with me. Try in your home. Will be 0. P0 is nothing but the probability that output will be 0. That P1 is that the output will be 1. So then what will be the probability of output now? That is the transition from output the P0 to 1. That is P1 will be what? So both are same only, I get the output like P0 and the P1. See, the probability of occurrence will be like 0 and 1 is same. So the probability of occurrence 0 to transition will be equal to P0 and 1 1. The P0 is nothing but the probability of the output will be 0. The P1 is nothing but the probability of the output will be equal to 1. Okay. Now this can be rewritten as. How can I write this one? I can write as in this way like P0 1 minus P0, because at a time you will get either 0 or 1 only you will get. You won't get the both output. So let us take the example. Let me take example. The example says, let me take an example. Okay. So now the example is, I can take example. So I'm going to consider 2-input NAND gate. Okay, so the NAND gate has 2 input, that is A and B, the output is. So now let me go for the truth table. A, B and the output is Y. 0, 0, 0, 1 and 0, 1. What is the output for NAND gate? This will be 1, this is 1, this is also 1, this will be 0. Now you can see here, then I will get the 0 output. So here, right? This is my 0, this B. What is the probability of occurrence of 0? That is P0, correct? No? So the P0 is equal to, so the probability of occurrence, the output is 0 is what? Like out of 4 combinations, you get only 1. So 1 by 4. Same the way, what is the probability of occurrence? The output is 1. The 1 will be 3 by 4. Then what will be your the probability of occurrence of the output? That is P0 to 1 is nothing but P0 into P1. So that will be 1 by 4 into 3 by 4. So I'll get is equal to 1. So this is what, right? 1 by 4 and the 3 by 4. So this is the transition I can say. So now this is for 2 input. I go by. So now from this I can say, what is the switching at 1 by 4 into 3 by 4? Then this will be 3 by 16. This is my 3 by 16. So simple I can say the switching activity. This is nothing but a switching activity. This is switching, but yeah, the switching activity 0 to 1 transition is 3 by 16. So this is for only for 2 input. Now let me take for n input gate. That is for only 2 input I said, right? If the input is n number, then what about the total number? The number of combination, the total number of combination is 2 to the power n actually. So out of 2 to the power n combinations in the truth table, let n0 be total number of combinations for which the output is 0. That is n1, n0. Okay, so let me take n1 now. The n1, same, the n1 also, the total number of combinations for which the output is 1. Now you can see this. Now how can I write for n input? Then it will become as like this. So like P0 will be is equal to n0. That is nothing but n0 is nothing but total number of combinations. The output will be 0. Then divided by the total number of combinations is 2 to the power n. So similarly, and what is P1? The P1 also like n1 divided by 2 power n. So what is the n1 here? Where n1 I can write as like this. n1 is equal to 2 to the power n minus n0. Even we can write like this also. So now what we can do? We can simplify this formula now. we get the transition, the switching activity from 0 to 1. That is P 0 to 1 means the switching activity 0 to 1. What is the switching activity 0 to 1? That is nothing but P0 and the P1. Correct? P0 and the P1. Where P0 is nothing but N0 by 2 power N into N1 by 2 power N. So again I can write as N0 by 2 power N into N1 is nothing but I can write as 2 to the power minus N0 divided by 2 to the power n. So this can be written as in general. The formula will be for n input gate. In general, I can write 2 to the 1 is equal to n naught into 2 to the power n naught divided by 2 to the power n. So this will be the formula to calculate the switching activity for n input. Say example, I will say, let me take example, okay? Example like 3 input NOR gate. For 3 input NOR gate, you tell me what is the probability occurrence of 0 actually? P0. P0 will be is equal to what is the formula? N0 by 2 power n. N0 by 2 power n means first of all we need to know the truth table, correct? No? So we need to know the truth table. So let me write the truth table. A, B, C, then Y. Let me write the truth table. 0, 0, 0. Output is 0, 0, 1. 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, then 1, 1, 1. Now what is the output? What is the output is 1. Then this will be, this also is 1 only, this also is 1 only, this also 1, this also 1, NOR gate, okay? Sorry, NOR gate, no? 0, 0, 0, this is 0. What about this 1, 0, 0? After that, 1, 0, 1 also 0. Next 1, 1, 0 also 0. This also 0. Now you can see only all the inputs are 0, the output is high. Any one of the input is high, then your output will be 0. So now from this what we can say, see here 0. So now I can say from this the number of occurrences will be like N0 will be only 1, right? So let me write what is P0 now. P0 will be 1 divided by 2 power n, it's nothing but 8, right? Next what about P1? The PA1 is nothing but how many will be there? Rest of the things are 0. So I can say 7 by 8. So now my switching activity from 0 to 1 is P0 into P1, then that will be 1 by 8 into 7 by 8. So this will be 7 by 64. The probability of that is switching activity. So same thing similarly, just you can apply in this formula and you can check that N0 is nothing but 1, correct? Then 2 to the power 3 minus N0 again 1 divided by 2 to the power 3. So what you get? 1, 8 minus 1 divided by 8. So 0 to 1, the activity will be what? This is total, okay? This is total activity I am saying. 7 by 8. See, I am getting for activities for this is P1 actually. This is for 1. That transfers from 0 to 1 actually. So for P0, the value is, for P0 value is what? P0 is, I think already given n naught by 2 power n. So in this way, we can calculate the switching activity. So now what we will do, let us take the example for two input, or let me put a so for example, okay, so for example, so as I mentioned earlier, so what we can do in the sense, we can consider for NAND and NOR gates. So I will put the activity that is for gate. Okay, so okay, I don't know that. Okay, for example, first inverter. So for inverter, for example, first for inverter, that is for NOR gate, NOT gate. Okay, for NOT gate, what is the probability will get? Like input is equal to 0, output will be 1. If the input is 1 is output is 0, then I will get the transition from P0 to 1 will is equal to. So second will be for two input NAND gate and AND gate. Then further we have this is 3 by 16 will get. Then third is two input NOR gate or OR gate. For this the switching activity will be again 3 by 16. But see, from this one thing I will say, the fourth one I will go as XOR gate. Now we need to see about XOR gate, what will happen. Okay, so before I write this here, let me put this here. So for XOR gate, for XOR. So as you know, what is the truth table of XOR gate? XOR gate is actually the A input and B input. Like we cannot say like if both the inputs are 0 or any one input is 1 low. We cannot say the output as high or low or something. But the very important thing, we can write the truth table here. It is not independent of the number of inputs. Your XOR, all the other gates are, it's a dependent on the number of inputs, but here it is not independent of the number of inputs. The output activities for different gates as well. But the variation of the switching activity or the output of XOR gate, let me say XOR gate to table A, B and Y, 0, 0, 0, 1, 1, 0, 1, 1. This will be 0, this will be 1, this will be 1, this will be 0. Now from this I can say if odd number of ones in the input, then output is high, else down. So from this I can say it will be very easy. Number of ones, odd number and the even numbers. So for that what I can do in the sense, let me say what will be the probability of occurrence. What is the P0 here? The P0 is nothing but the probability of occurrence 0 is 2, right? So 2 by 4. What is the probability of occurrence 1? The probability of occurrence 1 also is 2 by 4 only, because 2 ones we are getting. Then what is the switching activity of the both? The probability of occurrence 0 and 1 is nothing but 2 by 4 and 2 by 4, that will be 4 by 16, that will be 1 by 4. So irrespective of the number of gates, number of inputs in cases for XOR gate, we will get the probability of occurrence of the switching activity will be 1 by 4 only we will get. So from this I can draw the gate. One simple diagram I will draw, or I will show the diagram. I'll show the diagram. See, this will be your inputs. Your y-axis is nothing but your switching activity. Okay, this is switching activity. Now we can say number of inputs 2, 3, 4, number of inputs 5, 6, 7, 8. Now you can see for 2 input NAND gate or NOR gate, NAND gate. You can see here what is the probability I got here for 2 input 3 by 16 we got. I hope previously you can see 3 by 16 for 2 input. Alright, 3 by 16. For 3 input we got here we got how much? 7 by 64. You can see here what happening now. As the number of input increases, the switching activity is getting reduced. So now from that I can say how we get this your curve actually. Your curve will become as this is 0.0, this will be your 0.1, this will be your 0.2, this will be your 1 by 4, this will be your 0.3. This 1 by 4 is nothing but simple, I can say this is 1 by 4 actually. This is for your XOR gate. Irrespective of number of inputs, your XOR gate the switching activity will be 1 by 4 only. But if the input is for other gates, okay, so I will get like this. It is not linear, it is like somewhat in this way. It will go like this. This is for other gates. So this is the variation. The figure shows the switching activity. This figure shows switching activity for various inputs. Okay. Increase in the number of inputs. Okay. So now in this figure, now we shown only this is for static CMOS gates. Okay. Now let me say if the switching activity for complex logic gates. Switching activity for complex logic gates. Okay, so complex logic gates in the sense, you know the example. What is that? Y is equal to A plus BC. So like this, the complex logic gates example. Okay, so now for the complex logic gates, the switching activity depends on two factors. Depends on two factors actually. So which are the factors? The first factor is the topology of the gate. Topology of the gate. The second factor is statistical timing behavior. Timing behavior of the circuit. Now these two are the switching activity for complex logic gates. Now to handle this transition rate variation statistically, so let us consider for let n of n be the number of 0 to VDD output transitions. Output transitions in the time interval between 0 to n actually. Now let us go for the total energy E from supply for this. The total energy En, total energy is En, drawn from the power supply. From the power supply for this interval, which interval? For 0 to n actually. For this interval will given by En is equal to Cl into VDD square. This already we know, right? Cl VD square into the number of inputs like for complex schedule. N into n by. So I will consider this is equation number 1 now. Now what I need to do? You have to go for the average power dissipation. The average power dissipation, that is P average, I can say. Average power dissipation during an extended interval. Yes, that is P average will be, that is for large number of cans I can say, okay, that is limit n tends to infinity En divided by n into f. This is for large value of n for input, where f is frequency, as you know that, okay. Here this f is a clock frequency. F I can write, or I can write as fc. Okay. Now what you will do? Let us say the P average is equal to now substitute. This is equation number 2, right? Now what you do? Substitute 1 in 2. So what I'll get? Limit n tends to infinity, where the En is nothing but Cl VDD square by n into n of n into FCLK, right? Now just do some little work here, like changing the limit n tends to n. So I will take n of n divided by the capital of N into Cl into VDD square into clock. Now this term, which term?
So keep in mind these things. Using those things
See, now what about this term actually? This term is nothing but, I can say, the complete term, okay. Yes, this whole term I can say n by n is gives us the expected value of number of transitions per cycle. This one will be, the term will be expected or average. Is a expected or average value of the number of transitions per clock cycle. Transitions per clock cycle. So which will be defined by, it's a switching activity actually. It is a switching activity actually. So I will say where this alpha not 1, that is switching activity, right, is equal to limit n tends to infinity, this one capital N, okay, small n I1 n N divided by N is the switching activity factor. Now taking this term also into the account to get the complete expression for dynamic power consumption or the switching activity, I can say, right? P switch, or I can say PD will be is equal to, let's say first, alpha 0 CL VDD square F clock plus, see, remember this one, plus summation, the internal also we have to see, I is equal to 1 to K alpha I C I VDD then FCLK. See here, as you know, this is the complete formula to calculate the dynamic power consumption, where this will be your load capacitance, right? And the output load. This is for load. This is for internal load. Now from this we can understood that we want to know where this, what is alpha, right? What is alpha naught? The alpha naught is nothing but it is here switching activity at the output node. Remember that. But the alpha I is the switching activity at the ith node. At the ith node, where F is a clock frequency. Now we can say the power dissipation or the dynamic power dissipation, it purely depends on four factors. Which are the factors? The one is nothing but the factor number 1, switching activity factor. The second factor is load capacity, that is the capacitance. The third factor is VDD, that is nothing but your power supply. The fourth factor is clock frequency. Now, if you are reducing any one factor, then automatically the dynamic power dissipation will get reduced. So these are the four very important K factors. This is nothing but the switching activity for the complex logic gate. Next, what we will do, let us study about that if the inputs are not equiprobable, means like the probability of occurrence is not the same. So let me write the inputs are not equiprobable. If the inputs are not equiprobable, means so the probability of occurrence is not same. Probability of occurrence not same. By the situation, then what will be your switching activity? Now here, so far, we have assumed that the inputs are independent of each other and equiprobable. But input might not be equiprobable. So at this such cases, the probability of transition at the output will be depend on the probability of transition at the primary inputs. Let us consider, so here I will say, how can I say, let us consider, the NAND gate, 2 input NAND gate with the input A and B having mutually independent signal probability. NAND gate
same thing, right? What will be the maximum?
Having mutually independent signal probabilities of PA and PB. Okay. So let me say here two things. Just I'll put the diagram there. Okay. So we have considered the NAND gate. This is your PA. This will be your PB. Okay. So now output add this. Now we can see. I have to select PA. See what is a PA? I'll say this is output. P0 or a P1 or I can say P0. So now P0 will be is equal to 1 when PA and PB is equal to 1, then only I will get PA and PB both has to be 1. Sorry, this is I do it like this. P0 will be equal to 1 when actually when the PA dot PB should be is equal to 1, then only I will get the P output should be 1. PA dot PB should be 1. In the sense you can say here any one input or I can say in some other way I'll say let me write that the probability of logical 0, the probability of logical 0 at the output is, that is P0, right? P0 will be is equal to PA and PB. P naught is equal to 1. When I'll get 1? When PA and PB is equal to 1. Logically 0 I'll get, right? 0, sorry. This is 0 I'll get. Yeah, I'm mistake 1. Same the way, the probability of logical 1 at the output, probability of 1 at the output is, that is P1. What will be P1 now? P1 will be is equal to 1 minus P naught actually, right? Because it will be like, now what I can do, this P1 I can write as 1 minus PA P. I can write like this. Now what will be the switching activity? The switching activity. So therefore the switching activity will be like a P0 like P naught under P1, right? So the P naught is nothing but 1 minus PA P P. PAPB, right? P naught is nothing but PAPB, then P1 is nothing but 1 minus PAPB. So 1 minus PAPB into PA dot PB. This is the switching activity. So in similar way, similarly, the switching activity for 2 input NOR gate. For 2 input NOR gate actually how it will be like, the output is 1 when both the inputs are 0. I hope it's clear, right? Both the outputs are, that is both the inputs are 0, then only I will get the output is 1. So this is like EQ problem, right? The probability we cannot say like the probability of occurrence is not the same. So for such cases actually. So how we can write this expression now? The expression can be written as like this first. Let me write P1.
Probability of finding the particle is maximum.
So now what is the P1? So the P1 will be like P1 is nothing but I will get as like this 1 minus PA into 1 minus PB. Now you can see you apply PA and PB both. So like 0, 0 or 1, 1. So you will get the probability of 1 when it will get occurs. So similarly for P0 I will get what is P0? P0 is nothing but 1 minus P1.
Can you do the n is equal to 4?
Okay, 1 minus P1, that is P0. So this is nothing but 1 minus 1 minus PA, 1 minus PB. So now finally I can say the switching activity for P0 to 1. That is the switching activity P0 to 1 will be is equal to P0 1 into P0 1. So I will get as 1 minus PA 1 minus PB into 1 minus PA then 1 minus PB. So this will be the switching activity for P02. So in this manner we can calculate the switching activity at the output for any complex gate can be obtained. So for the output switching activity for the different gates. So let me show how it will be for complex logic gate. That is for normal static gate. Okay. For complex logic gate. For complex, if the inputs are not EQ probable, then so I have that like for NAND or AND gate. NAND and AND gate, then what will be the switching activity for P0 to 1 will be is equal to PA PB into 1 minus PA PB. This is already we wrote. Same for NOR or OR gate. 1 minus, that is for again transition P0 to 1, like 1 minus PA 1 minus PB then 1 minus PA 1 minus PB. Next for XOR gate. So for XOR gate the switching activity will be 1 minus PA plus PB minus 2 times of PA into PB, then PA plus PB minus 2 times of PA PB. This is the switching activity of different gates, or I can say for EQ probable inputs for the logic gates. Okay, so now what we will do next, we will see mutually dependent input. mutually dependent input. Okay, mutually dependent input. Okay. Now for mutually dependent input in the sense like for multi-level network, this is for multi-level network. Multi-level network means like a one for network of complex logic gates. Say example, one gate will drive the another gate. Sometimes what will happen, the output will be depends on the previous. Correct? It's not like the output very simple. I can say you are each and every stages. The output will be dependent on the previous. So like mutual, the input gates are like something like I want to say like the input to a gate input to a gate at a particular stage. At a particular stage might not be independent. When it will happen like this, so this will happen because of the signal from one input may propagate to multi. When it will happen, when simple I can say like it will happen because the signal from one input may propagate through multiple paths and again recombine. Means like a more number of fan-ins will be there, the fan-out again will be recombined at a particular stage. This is the meaning of that actually. Now here we can say there will be some two problems. That problem only we can call as reconvergent fan-out. Like you know that the fan-in and the fan-out two terms. I think you might have heard about fan-in, fan-out. The number of inputs drive the gate is fan-in. The number of the outputs drive that is nothing but fan-out. Right. So here the very important thing here. So what we'll do, we need to consider the diagram as this. Let us consider the figure.
Still there is a probability that psi is non-zero. So psi has some definite, some value is there. So if psi has some value,
We are considering
so how many regions are there in this
see 2 NOR gate, right? This is input is x1, x2, x3, x4. Okay, so now again this output we are connecting to the another one more NOR gate. This is what we said. The signal from one input may propagate through the multiple path and recombine and it will produce the output stage. So this stage, so I will say this will be your A, this is B, this is C, this is D, this will be E, this will be F, this will be your G. Now what we will do, let us say that x1 and x1 and x2, let the x1, x2, x4, these all four are independent of each other.
you see there are two energies here. One is E, which is the energy of the particle. Another is the
Okay, independent of each other. Now we see what will be the probability the occurrence at E and what will be the probability occurrence at F. Very clear, remember this is two input, okay, but the number of input we are applying is a 4 bit, it's a 4 variable input, right? So what will be the probability of occurrence, the output of NOR gate here? What will be the probability of occurrence. So I'll say here in this place, what will be? That is, I'll say the P0 and P1, correct? Both are like what? Both are both are NOR gate only, right? So P0, P1. So the P0, P1. So what will be the probability of occurrence we get now? So any idea? I got?
If I increase the energy of the particle and barrier weight is fixed, what should happen?
Any idea?
What will you guess? Can you guess what will happen?
How much the probability of occurrence will happen? So simple, I can say here the probability of occurrence will be 3 by 16. Here also probability of occurrence 3 by 16. We have to apply into the formula, previous formula. Okay. Now what about here? We'll get now. It's a 4, right? 4 in the sense the number of ones and number of the zeros. So 4 bits 16. So I can say the output finally I will get here normally. Actually what I should get here in the sense 9 by 16 into 7 by 16. So I will get as 63 by 256 because it's a 4 input, 4 variable. So 16 combination, 2 port combination, right? So now you can see that as you know that the transisting activity from P0 to P0 into P1. So the P0 is 9 by 16, P1 is 7 by 16. But intermediate signal can be anything. So like I can say, finally recombine and get 63 by 256. Now what I'm doing here in the sense like this is circuit without reconvergent fan out actually. This is called as this circuit is called as this circuit is called as without reconvergent fan out. Now you may see fan out is which is the fan out you may have to write which is the fan out here. This is fan out actually. Okay, this will be your fan out. Now what I'm doing, I'm going to merge this like instead of giving the circuit as like this, I want to draw or modifying this circuit as 1, 2, 3, 4. Correct? Okay. This is one gate. See here, x1, x2, x3. Again, this is driving a NOR gate. Now you can see the variable here you are giving is 3. But okay, x1, x2, x3 only here. But here we are having 4 input actually. So the 4 input in the sense as the for NOR gate 3 by 16 only, this is also 3 by 16. This is already we see in the previous tables. Okay, the probability of occurrence. So now this will be your V, this is your F, this will be G. Now you can say, but here happened because of this short circuit. Because of this short circuit here we don't know. Because of this what will happen automatically this will get reduced. So even this is 0, this also will become 0. So I can minimize this with a 3 variable. So my probability of occurrence I will get 3 by 8 into 5 by 8 will be is equal to 15 by 64. So this circuit actually, this figure is like a circuit with reconvergent fan out, because when you write the combinations, like sometimes what will happen, these two will be more long, you will say. So now that is the reason they written in this way. So now we can see in this like we see in the computations of the transition probability. So started from the primary inputs and we calculated the signal probabilities till the output node is reached. But this approach will not work for circuits having reconvergent fan out. That is why I said for this, which one? For this, it won't work out. If you do this, it won't work out. So that is the reason actually what will happen. We done the inter-signal dependencies. It's like leading to different switching activities at the node G. So we got this like the input E and the F are mutually dependent. The input E and the F are mutually dependent. So this is all about today's class. So what we'll do the next class, we'll study about the transition probability in dynamic gates.